Let us now understand what we mean by dominance of heuristics. Let us say we have two admissible heuristics, H sub 1 and H sub 2. If for any node n, all these nodes that I am talking of, the heuristic value H sub 2 is more than, for two admissible heuristics H sub 1 and H sub 2, if H sub n is more than equal to H sub 1 n for all n, then H sub 2 dominates H sub 1. H sub 2 is better for such. A heuristic H sub a is better than another heuristic H sub b, that is H a dominates H b if for all nodes H a is more than equal to H b. For the 8 puzzle game, we had highlighted two heuristics, if you remember, the total of the Manhattan distances and the total of the misplaced tiles. The Manhattan distance dominates the Hamming distance heuristics. Let us now move on to understand what we mean by composite heuristics. We have, let us say, a couple of heuristics. We do not know which heuristic dominates which other. Then the maximum of two admissible heuristics is also admissible. Going by that, if we develop two or more heuristics for the same problem and we are unsure whether any of them dominates all others, we can use the maximum of them as the composite heuristic. This composite heuristic will take more time to compute, but would be more accurate. This is what makes composite heuristics interesting. Let us now look at more closely another heuristic that is referred to as consistent heuristic. Consistent heuristics are those which places even stricter constraints on the heuristic. It requires that the heuristic estimate must be greater than the actual cost for each arc along a path. So one consequence of this is that the final value that I compute for a node to reach to the goal never decreases along a path to the goal. Consistency therefore implies admissibility. That is, a consistent heuristic is also admissible. However, the opposite is not necessarily true. Most admissible heuristics are consistent, especially if from relaxed problems. So let us look at what we mean by consistent heuristic. Let us say we have the cost to a node given to us from n to this given node, or if the total cost to the goal is hn, and hn can be looked at given another successor node odd n prime of n generated for any n, hn would be the cost of coming from n to n prime because of an action A, and then going down by an estimate at n prime, which is h and s to g. If h is consistent, we have the total cost of arriving at the goal from n prime to be the cost of coming to n prime, which is g n prime, and then the estimate of going from n prime to g, which is h n prime. But we have already seen that g n prime, the total cost, is about the total cost at n plus the cost because of action A on n to n prime. So that we can substitute here, g n prime getting substituted by g n, c n, a n prime, and h n prime is the estimate that's already added. Now given g n, c n and n prime plus h n to be greater than or equal to h n, the f dash n that we have is actually greater than equal to g n plus h n, and this is nothing but f n, the cost at node n of coming here. So f n we see is non-decreasing along any path. So let us look back on what we said about consistent heuristics. that it puts stricter constraints, no doubt, but once we have that consistent heuristic, the f value never decreases along a path to the goal. Finally, we want to take two notes that heuristics is actually a trade-off between quality of estimate and work per node. As heuristics get closer to the true cost, we expand fewer nodes, but usually do more work per node to compute the heuristic itself. At the two extremes are the null heuristic, which always returns 0 and requires the least amount of work, and the exact cost, which can only be found by conducting search itself and requires the most amount of work. Choosing a good heuristic is therefore a very vital problem. For any given problem, there might be many different heuristics one can choose. However, some heuristics are better than others. We say heuristics is better if it needs few nodes to examine in the search tree. We also call these kinds of heuristics are better informed. Efficiency is very important in picking a heuristic. It is very important to consider the efficiency of running the heuristic itself. More information about a problem would mean more time to process the information and maybe more inefficient heuristics. So while we look at informed search strategies in our next lecture, we would also once again look back on heuristics. Today, the lecture was on understanding what heuristics are, what is the motivation of using heuristics, and giving a couple of properties. A, what do we mean by admissible heuristic? B, what is dominance? C, what do we mean by a consistent heuristics? Thank you very much.